So our next step is to determine the connection between the equilibrium constant and the free energy of a reaction. And we've already done this once for one example when we were talking about the H2 plus Br2 reaction yielding two HBRs, but that was back when we were working only with simple cases where the number of molecules on the reactant side was equal to the number of molecules on the product side. So we need to make sure we understand how it's going to work when there's a change in the number of molecules during a reaction. So we'll go back and start with the equilibrium condition, the starting point here. So in other words, the sum of the chemical potentials times their stoichiometric coefficients has to be zero. Stated a little more plainly, what that says is chemical potential of the products minus chemical potential of the reactants has to be zero, or saying it one more time, the chemical potential of the reactants has to be the same as the chemical potential of the products. That's what makes the reaction in equilibrium. There's no change in the chemical potential when reactants convert to products or vice versa. So we can remember that the chemical potential is, under some set of conditions, is the standard state chemical potential plus RT log of the activity. If we're specifically talking about ideal gases, then activity is pressure over standard pressure. Activity is mole fraction, which is the same as pressure over standard pressure. So if I take that expression for the chemical potential of a gas, an ideal gas, and insert it into the equilibrium condition, then the equilibrium condition becomes sum of nu times this mu naught plus RT log of P over P naught. Breaking those two terms up, the first term looks like the sum of stoichiometry coefficients times standard chemical potential. The second sum looks like stoichiometry coefficients times the RT log P over P naught term. If I take this term and I move it to the other side of the equation, then I've got negative, pulling the RT out of the sum, negative RT times the sum of the stoichiometric coefficients times log of P over P naught. This constant nu times a log is equal to the log of the quantity raised to the nu power. So if I use the log rules one more time, the sum of all these logs is the log of the product. So what I've got in this step right here is I've got minus RT times the log of pressure of products over P naught raised to their stoichiometric coefficients times pressure of reactants over P naught raised to their stoichiometric coefficients, and remembering those are going to be negative for reactants. And on the right side, I've turned this sum of standard chemical potential of products minus standard chemical potential of reactants, remembering that chemical potential is the same as partial molar free energy. If I'm doing things at constant pressure and constant temperature, then it's standard molar Gibbs free energy. So in this step, I've assumed constant T and constant P. So that I can write it as partial molar Gibbs free energy. If I were doing it under different conditions, I could use partial molar Helmholtz energy or some different energy. So I've got a minus RT on the left that I can divide over and get it into the denominator on the right. So now on the left, all I have is a log. So if I undo that log by exponentiating both sides, I've got the product of these pressures on the left is equal to E to the minus delta G over RT on the right. The P naught pressure, that should actually be a superscript P naught instead of a subscript P naught. Standard pressure, if I pull that out of the product, so that I've got 1 over P naught raised to the delta nu times this product of pressures raised to the stoichiometric coefficients, that term finally begins to look like an equilibrium constant. So if I take the P naughts and I move them over to the right side of the equation, what I find is that the equilibrium constant Kp is equal to e to the minus delta G over RT times standard pressure raised to the delta nu. So this is the same result we originally had for the H2 plus Br2 reaction. In that case, delta nu was 0, so we didn't have this last term. The purpose of this final term is, again, essentially as a unit correction. This e to the minus delta G over RT term, that's unitless, like any exponential. A Kp, remember that's pressures of products over pressures of reactants. So if I have more products than reactants, that's going to have units of pressure raised to some power. If I have fewer products than reactants, it's going to be pressure raised to some negative power. So that's the purpose of this term here. P naught, this is usually a pretty boring term if you're doing things where you've defined standard pressure to be 1 atmosphere or 1 bar. This is just a pressure of 1 in some units raised to some power. So it's only there to tack some units onto this unitless quantity that you get from doing e to the minus delta G naught over RT. To work an example with that equation and make sure it's clear, let's take a reaction where we have a different number of products than reactants. Let's say we react nitrogen gas and hydrogen gas to form ammonia gas. So 4 molecules of reactants form 2 molecules of products. So in this case, our change in number of moles is going to be -2. I lose 2 moles of gas every time the reaction proceeds 1 mole of times. And we're given that the free energy of formation, the Gibbs free energy of formation for 1 mole of ammonia is -16.4 kilojoules per mole. And we'd like to know what is Kp at 298 Kelvin. So first step is to calculate delta G of the reaction. So that's free energies of products minus free energies of reactants. So twice the free energy of NH3 minus the free energy of N2 minus 3 times the free energy of H2. And again, each of these numbers comes from the stoichiometry of the reaction. We're given the Gibbs free energy of formation for ammonia, -16.4. We don't need to be given the free energies of formation of nitrogen or hydrogen because those are elements in their standard states in the gaseous state. So the free energy of formation of any element in its standard state is 0. So we just subtract some zeros from the free energies of formation of 2 moles of ammonia. So the total free energy of the reaction is -32.8 kilojoules per mole, twice the free energy of formation of ammonia, because this is essentially a formation reaction for forming 2 moles of ammonia instead of 1 mole. Now that we have delta G, we can calculate the equilibrium constant is e to the minus delta G over RT, not forgetting to put in this P naught term to make sure the units come out right. So e to the minus 32.8 kilojoules per mole, or 32,800 joules per mole, divided by R divided by T. In this exponential, multiplying by standard pressure, which I've taken to be 1 atmosphere for this example, where these standard free energies of formation were obtained, raised to the delta nu. We lose 2 moles of gas for every time the reaction proceeds 1 mole of times. So if we plug those numbers into the calculator, what we find is that the numerical value is 560,000, 5.6 times 10 to the 5th is our value of Kp, and it has units of 1 over atmospheres squared from this term. And again, the units are there just because the Kp is going to look like pressures of products, so 2 pressures in the numerator divided by pressures of reactants, and I've got 4 different quantities with units of pressure in the denominator. So overall, the units of a Kp is always going to come out in 1 over pressure squared. So that's a numerical example that shows us how to calculate a Kp. Really, the only difference between this equation and the one you're more familiar with from general chemistry is we have this new term, the P naught raised to the delta nu, to keep our units straight, but converting back and forth between equilibrium constants and free energies is relatively straightforward with this equation. In fact, usually what we do is not what was done in this problem. Usually in lab we can set up a reaction and measure how far it goes towards completion, measure how much of each product and reactant we have, calculate a Kp value from that, and then that's often how we can calculate a delta G for the reaction. The change in the free energy for the reaction is from the Kp that we can measure fairly easily experimentally.